The voltage divider circuits, remember, are these circuits which split the battery voltage between the two resistors depending on the value of resistance. So a bigger resistor will get a proportionately bigger voltage. It needs that extra voltage to produce the same current through both. And usually in electronics, they're not drawn with a battery, but you've got what are called supply rails, but a line along the top connected to the positive end of the battery, and then you've got your two resistors. Now in these sensor circuits that we're looking at, the idea is that one of these resistors will respond to changes in real world conditions. So rather than being two fixed resistors like I've drawn there, you might have one which is a thermistor, one which is an LDR. So if we look at the thermistor circuits first of all, we'll draw the thermistor down the bottom, and the top is just a fixed resistor. You'll often see it as a variable resistor, and that just, we'll see why later, basically why that's important. So I'm connecting my voltmeter across the bottom, which is usual for reasons we'll see when we go on as well. And we need to describe how this circuit would respond to changes. Now you need to be able to adapt this, but often the question will be based around it. So explain how this circuit operates, or explain what happens when the temperature drops. So you often have to start like that. So when the temperature falls, that's kind of implied in the question, and then you now need to look to your circuit and say, well, what's going to change when the temperature changes? Well, that's what a thermistor is. It's a temperature dependent resistor, so that's where we start our description. And you need to know the factual stuff about thermistors and LDRs. So you need to know this first step. So for instance, when the temperature falls, the resistance of the thermistor increases. Now one useful way to remember that for both thermistors and LDRs, less energy going in, whether it's heat or light, then higher resistance. So the resistance of the thermistor increases, but that's the initial thing that changes, but what we're interested in is what happens to the voltages in the circuit. And what we've got then is this idea that in these voltage divider circuits, voltage and resistance are proportional. So if a resistance increases, a voltage will increase. But we always need to be precise about which resistance we're talking about, which voltage we're talking about. So we use this phrase, the voltage across the thermistor would also increase. Now your voltmeter here is connected across the thermistor, so the last bit we can clarify is the voltmeter reading increases. Basically we've got something that provides a bigger voltage the colder it gets. So we could almost think of that as a coldness sensor, right, or a cold sensor. So we'll label that accordingly. So this is our cold sensor. Now, how could we turn it into a hot sensor? Okay, the cold sensor can be useful if you're interested in things like heating systems, for instance, when you want to know when it's getting cold. But we're also interested in things like, say, climate control and knowing when things get hot. And remember that one of the ideas we looked at in a voltage divider circuit is that, well, the voltage is proportional to the resistance. So if I swap the position of these two resistors, it's going to change how the circuit acts. Now for a bit of speed here, and because it's difficult on an iPad, I am drawing these resistors freehand, so they are a wee bit messy. This time I'm putting the thermistor up the top and leaving the voltmeter across the bottom. Now you could achieve a similar effect just by moving the voltmeter from top to bottom, but as we'll see in the next section, it's usually the bottom voltage that we're interested in. And what we now have is a circuit, as we'll see in a wee second, which responds to rises in temperature. And as we wrote above, the resistance of the thermistor increases when the temperature falls. So when the temperature of the temperature rises, the resistance of the thermistor decreases. And the voltage therefore follows suit. It will also decrease. But our voltmeter isn't connected across the thermistor. So we now need to see what's happening to the voltage across the resistor. Now remember, these two resistors here and here, both their voltages will add up to supply voltage. It's a simple series circuit. Right? A voltmeter won't affect that, having a voltmeter in parallel. So these two voltages add up. So if the thermistor is taking a smaller voltage, that leaves a bigger share for the resistor. So even though its resistance hasn't changed, because the other resistor has changed, it's changed the balance between the two. So it's changed the split of the voltage. So the final step is to say that the voltage across the thermistor decreases. So the voltage across the resistor will increase. And that's where our voltmeter is connected, so the voltmeter reading increases. So we've got our heat sensor, or hot sensor, whatever you want to call it. Now either of these circuits, you could also explain the opposite way around. So what happens to the first circuit when the temperature rises, what happens to the second circuit when the temperature falls, and you would just reverse all the increases and decreases and so on. So that's our temperature dependent ones, and moving on to our light dependent ones. So now we'll look at circuits with LDRs in them, same sort of idea again. Two resistors. I'm going to make this one an LDR, so a couple of arrows into it. It's a symbol for an LDR. And when light levels fall, our starting fact about LDRs is that their resistance increases. Once again, notice I'm avoiding writing down the resistance. I'm always being clear about what resistance I'm talking about. And the same for voltage. So it's always the voltage across something we talk about. If you ever write voltage flowing, you'll find in marking schemes 0 marks written besides phrases like that. Okay, voltage is a difference between the positive and negative that causes electrons to flow, but voltage itself never flows. And the voltage will follow the same pattern as what's happened to the resistance. So it will also increase in this case. And our voltmeter is connected across the LDR, so the voltmeter reading increases. So we've got a dark sensor, right? We've got a circuit which increases in voltage the darker it gets. And then similar sort of idea, how can we turn it into a light sensor? If we swap the position of the LDR and the fixed resistor, just notice I've missed out a T there, and usually they're written with a plus as well. So if we start a new screen and swap positions this time, then we should get a circuit which acts in the opposite way. This time we've got the fixed resistor at the bottom and the LDR at the top, plus VS and 0 volts as usual. And this is going to be a light sensor, so when light levels rise, the resistance of the LDR decreases. And that means the voltage will follow the same pattern. Voltage and resistance are proportional. And the voltage across the LDR decreases. But our voltmeter isn't connected across LDR, so we now need to, with this one, think about the idea that they are sharing that supply voltage between them. So if the LDR is taking a smaller share of the voltage, then the voltage across the resistor will increase. And the voltmeter is connected across the resistor, so the voltmeter reading increases. And we've got a light sensor. It's actually more difficult to think of uses for something to switch on when it gets light. You could have, for instance, automatic blinds in a kind of smart building, that when the sunlight gets too bright, it closes blinds. Now, those 4 circuits that we've done there, we've covered all the possibilities. They're the most common ones which come up, right? Thermistors and LDR circuits. But the learning outcomes also mention 2 other types of circuits, which are switch circuits and capacitor circuits. So we'll do one example each of them. So a switch circuit, same sort of idea again, voltage divider, so 2 things in series, except one of them now is a switch rather than a resistor. I'm going to put the switch in the bottom half and connect our voltmeter there as well. So switch symbol, and we've got a resistor in the top half. 2 battery connections. Okay, and for this we need to talk a wee bit just about what is a switch, what does it do? Well, it's quite a simple device. You either close the contacts and make them touch, right? They're made of metal, which is effectively no resistance. Or when it's open, you've got an air gap. Now, air has got a very high resistance. It's a good insulator. So, an open switch is a very high resistance, much higher than any fixed resistor in a circuit would be. So therefore, it's got the biggest share of the resistance and is going to take the biggest share of the voltage. So an open switch is a very high resistance. So the voltage across the switch will basically be taking all of the supply voltage. That's going to take basically the full share of that. And that's where our voltmeter is connected. So the voltmeter reads VS. A closed switch is just touching metal to metal. So ideally it would have no resistance. And if it's got no resistance, it will have no voltage. So the voltage across the switch is 0 volts and the voltmeter reads 0. Okay, fairly straightforward. It's a wee bit kind of back to front, that the voltage is high when the switch is open. When you close the switch, it goes down to 0, but it's all to do with resistance. And then the last one is we need to talk about a capacitor circuit. Same sort of idea again. Strictly speaking, this isn't really a potential divider because we're not talking about the resistance of a capacitor. But we'll just describe it. It looks very similar circuit. It's not very well drawn. There's our voltmeter. A symbol for a capacitor we met earlier on. It's 2 parallel lines. Try that again. And a capacitor, we wrote way back in one of the previous chapters, its function is to store charge. So basically when you switch on this circuit, the capacitor is going to start storing charge. It's a bit like a jug that you're filling with water. It doesn't do it instantly, it doesn't fill up instantly. So when the circuit is switched on, and you often will actually see a switch added in to these circuits, the capacitor starts to fill up. And what happens then is that the voltage across the capacitor increases. But one of the key ideas is, depending on the values you've picked, but it will slowly increase as the capacitor fills up. Now this can be controlled by using different values of capacitor, what's called as a capacitance, or different values of resistor, i.e. resistance. So the voltmeter reading also slowly increases because it's connected across a capacitor. And this is used often as a time delay. Okay, so for instance, sometimes some cars have lights which switch on when you first get out the car and then switch off a short time later. So you would use a capacitor, actually looking at decreasing, so you put the capacitor up the top. But you get that time delay built into it. The speed with which it increases which the voltage increases, that's not a good word to use. And that's controlled by the value of capacitance, which is a measurement of a capacitor, and resistance, which basically reduces the current and therefore slows down how quickly it fills up. And if either of them is greater, then the time delay will be longer. So larger values give longer time delays.